Okay, so good afternoon, everyone. So welcome to this introductory course. And the name of the course is Demystifying Deep Learning, especially ChatGPT. I think most people are here because of the second sentence, the ChatGPT here. So I will try to, do some demystifying for you. And so my name is Richard. I'm from the Department of Math. And let's just get started. So just firstly, some very brief history of deep learning or the technologies leading up to deep learning. So which is artificial intelligence. Now, the dream of getting a machine to help human to do part of thinking has been around even since the ancient times, even since the Bronze Age. But it's only till the invention of the computers, which actually makes it possible. So during this time, between the 1980s to about 2008, this is what we call them a AI winter. So there was actually a lot of hype around about what computers can actually do for artificial intelligence, but there's not that many sort of significant progress that's been made during these times. And that's all about the change when we hit the milestone, which is around the year 2008. So does anyone know what happened in 2008? So I think a lot of people would try to guess that's the Beijing Olympic Games, but that's not entirely true for as far as AI is concerned. So in 2008, there was a very large data set. It's called the ImageNet that was being released by Stanford University. And that image data set containing 3 million images of 1,000 different classes. That's 3,000 images per class. So these different image classes encapsulating basically all the natural image categories, like a chair, a desk, a mouse, a smartphone, and so on and so forth. And so that particular competition has essentially sparked the growth of research in deep learning. And that particular competition has ended in year 2017. And the reason why it's ended is because people nowadays can actually achieve a much better recognition accuracy on the ImageNet dataset than a human vision. So there's no longer challenging for a competition purpose. And I think most people probably have heard of AlphaGo. So AlphaGo is essentially using reinforcement learning to beat the best Go player in the world, right? So that's also kind of sparked a lot of interest around about what AI can possibly do. This is kind of the growth of AI, which I kind of referring to as AI spring. But now I think we have reached AI summer. So I have summarized a lot of the milestone technologies that's happening around these times. So, I mean, for people who are sort of interested in AI and having been keeping up to date with the blogs and news about AI, probably you have heard some of these technologies. So I have break them down into 4 different categories. So the purple stuff is computer vision, and the green stuff are the technologies involving reinforcement learning. Now, the blue one, or the light blue one, is what we call the generative models. And lastly, but most importantly, which I think are what people are interested in most, are the yellow ones. The yellow ones are the technologies associated with natural language processing. And also, these are the deep learning packages that's released by the major players in this area, predominantly Google and Facebook AI. Now it's called Meta AI. Okay. Any questions so far? Please do let me know. You don't have to wait till the end to ask me questions. If you do want to share, please do raise your hand and have a bit of interaction. That's also interesting. Okay, so I think some of these technologies might be familiar to you. And with that said, people start wondering why all of a sudden deep learning becomes so popular. There are three contributing factors. The number one is the accessibility of data. So in the past, if you have a computer, the computer can only see all the data in itself. But these days, you have everything stored in the cloud. So theoretically, you will be able to have a computer be able to see all the world's data. That's pretty much like the case in ChatGPT, right? Because it actually has access to pretty much all the text data that the company is able to grab. And the second factor is that the algorithm becomes a lot better. So the number of researchers sort of have jumped onto the bandwagon of AI research has grown exponentially. So in the past, if we see a popular academic paper that attracts 100 citations in a year, that's actually a very phenomenal number. But these days, it's very often to see some academic papers being cited more than 30,000 times within a year. So that particular paper that particular technology I was referring to in the previous slides, the ResNet, it has been cited 140,000 times since its release, and that was only published in 2015. And lastly, there's availability of GPUs. So does anyone know what GPU used for prior to deep learning? I'm sure you play games, right? And especially games that involve 3D rendering. So what's GPU? How's GPU different to CPU is that GPU, you have lots of mini CPUs. They will be doing very sort of elementary computation, like matrix multiplication. But since you have thousands of them within a single chip, you will be able to perform these mini computations in parallel. So you can actually do a lot of simple calculations, but you can do a lot of them at the same time. So that's the advantage of GPU. And so companies like NVIDIA have realized that, the same chip design not only helps you to render your polygons of your games faster, it can also be used for training deep learning models. And so therefore, without too much of a sort of radical changes in their chip design, they have now provided the processing power that actually powers a lot of the state-of-art algorithms that you have seen these days. Okay. All right. So, and also some of the buzzwords you probably have here the words like AI, deep learning, machine learning all the time, and you probably wonder what are the difference between the three. So AI, artificial intelligence, is pretty much every single piece of technology that allows the machine to help human to the part of thinking, and that's AI technology. Now, machine learning is a subset of artificial intelligence. It's those technologies involving having a set of statistical and mathematical, algorithms that analyzes all the data it has access to, and be able to draw patterns from those data. So these patterns can be applied for future unseen data, where you can do things like prediction, inference, and so on and so forth. Okay, so that's the distinction between machine learning and AI. It's actually a subset of AI. Now, deep learning is a subset of machine learning. So it does virtually everything that machine learning does, except the algorithms involving deep learning will use neural networks. And in fact, lots and lots layers of neural networks. Okay, so that's the distinction between the three phrases, the three terminologies. And so please do let me know if you do have questions before I go on. Okay, all right. So I'm going to show you in a very simplistic form what convolution neural network does. And I'm sure that some of you probably have heard of CNN before, convolution neural networks. And that's the backbone of deep learning. So when CNN first came out, it actually, so CNN becomes, like I said in the past, like I said before, that CNN became the backbone of, say, image classification. And so what does it do? Just imagine that you try to build yourself a image classification algorithm that try to classify between photos of 10 people. So you have, say, 10 images of Sarah. You also have 10 images of John, for example. And now if you think about an image, what kind of a representation does the image have? Images are already represented in numerical form through the two-dimensional array of pixels, yeah? So what people tend to do is that they take a column of a pixel and they append to the second column and then append to the third column and so on and so forth. So you sort of get yourself a giant array of vector, which is an array of numbers. And then you will put this vector representation into an image classifier, okay, to classify, to get the machine to figure out which person is that this photo belongs to. Now, if you do that, you can sort of see that this representation is not very robust for classification purpose. Why? Because if you shift this pixel by one place to the right, it's hardly noticeable by a human, yeah? But if you do that for the machine will actually see this image being an entirely different image, yes? So therefore, that representation isn't robust against things like pixel shifting, light change, slight light changes, or we call it a slight illumination change, or slight rotation. These sort of operations are easily picked up by a human vision to recognize them being exactly the same image, but that's very difficult to do for the machine. So therefore, we do need to have a much more robust representation of the image. And deep neural networks basically does that. So in a simplistic form, this is what it does. This is the original representation of an image. Now, using neural network, you start to extract in the lower layers, which corresponds to, so this stuff, which corresponds to the elementary features of an image. So what are the elementary features of an image? So these are things corresponding to the lines, the patches, the colors and things and so on and so forth, yeah? So they also correspond to how the human vision system works. People believe that corresponds to our visual cortex, which kind of extracts the elementary image features. Now, moving on to the higher layers. In the middle layers, they represent the image patch or the, so in terms of a facial image, the image patch will represent things like the eyes, the eyebrows, the nose, the ears and cheeks, and so on and so forth, yeah? So at the highest layer, these neurons actually represent the entire face, okay? So by popping through this image, through this neural network of many layers, then once you have reached the highest layer, you obtained a much more robust representation of an image. So if you're doing things like pixel shifting, light distortion, slight image rotation, hopefully in this robust representation, they will be very much the same representation because you are still having exactly the same image, yeah? So in the end of the day, what convolution neural network does is give you a re-representation of your original data so that this form of data representation is much more robust for whatever task that you wanted to do. For example, image classification or regression. Okay, is that understood? Okay, so yeah, please do let me know if things are not clear to you. Okay, the second seminal research in modern neural networks is called recurrent neural networks, which I'm gonna deliberately skip for now, because when we talk about ChatGPT, we're actually gonna talk a lot about the RNN architecture. So I will elaborate further when we talk about ChatGPT. Okay, so the second part of the talk I'm going to talk about examples revolving around the four mainstreams of machine learning, namely computer vision, reinforcement learning, generative models, and natural language processing. Okay, so some of the take-home messages is machine learning is actually not that far away from university research than what you might think. So there's still a lot of areas where research needs to be done. And I have also selected amongst the thousands of applications, the few applications that I have worked on before. So that just makes it easy for you to sort of relate to it. Obviously, there are too many deep learning areas. I can only select a few that I actually knew or I'm more familiar with. So let's get started. So firstly, I would like to show you a few things that I've worked on a long time ago. That's like 18 years ago. And this is where deep learning, none of the deep learning algorithms exist. Actually, they have existed, but it's just not very popular. And I do not have any GPU support at the time. So I can sort of show you the performance. And then we will make a contrast to what happens when you do apply deep learning to these systems. So in here, what I'm trying to do is that I try to track my head in a pair of static camera. Static camera, I mean the camera once it's mounted, they cannot move. Okay, they are looking at the same direction, observing the same area. Because they have very large field of view, you are able to track the object of interest in each respective image view, and then you are able to deduce the 3D position of the object of interest. So in this particular case, it's the 3D position of my head. Then I use that information to start controlling this mechanical camera such that my head always appear in the center of the camera view. Okay, so that's what I'm trying to do. And I did that work back in 2015. And so how do I actually get the three cameras to agree? So this is what I did. I actually put a very large a whiteboard, very much like this one, and even slightly bigger. And so, okay, let me show you this one first. So this is the view from a static camera, which is not the camera that cannot mechanically move. So once I place a whiteboard in here, I basically will nominate, this is the camera coordinate system, and this has been the x-axis, this being the y-axis, and the perpendicular to it is the z-axis. Okay, and so by detecting all the images corners, I'll be able to figure out what does this 3D coordinate looks like from that static camera. And I will do the same thing for the PDZ camera, except PDZ camera is slightly harder to do. The reason is that every time I mechanically change the position or the orientation of the camera, they'll be looking at the camera center and the angle it points to will be different. So what I did is I wrote this software that allows the camera to pan, which is the motion horizontally, and tilt, which is the motion vertically. And so that once it actually reaches the center of the view, I will capture both the image coordinates as well as the mechanical position of the camera, so that I will do that for every subsequent settings. And I'll get the camera to move in a zigzag fashion as well. And so once I've done that, I do know that when I try to triangulate from the perostatic camera and figure out the 3D position, I can then just apply a very simple regression and be able to obtain the desired mechanical values so that my camera will be aiming at my head all the time. Okay, so you can see that the tracking and stuff isn't as robust as I would like to have. I also applied the similar kind of technology to other computer vision applications. So here's an example where I using a very similar setup in such a way that if I start video streaming this portion of the video to a distance education student, then people can't see it very, very clearly. Yeah. But if I able to control this mechanical camera, especially having its lens zoomed in, I will be able to scan the part of the region where the person has updated the whiteboard in such a way that I'm converting, using a pair of cameras, I'm converting a traditional whiteboard, looks like this, nothing fancy, just a whiteboard, into an electronic whiteboard. So that's the aim of that research. And it's actually achieved by 2 image warp from here to here and from here to here. And the trick is that you actually wanted to compute that matrix in one go. Otherwise, you will get a very blurry image. Okay, so this is all can be achieved without deep learning. And maybe this is the last one I'm going to show you before we actually move on to the deep learning approach. So here's a system I have built, which is called augmented reality. And that's what's done about 15 years ago. So what I try to do is that I will actually get a person to carry a physical real camera, but to film a virtual world. And so that what I did is that I mount a checkerboard on the side of the physical camera. And then I have an observing camera. The observing camera looks at this checkerboard. It figures out the position and the orientation of this camera. And also, even though these physical cameras do not function properly, we actually bought it from eBay for $50. But what we did is that we hardwired the zoom in and the zoom out button. We put a battery to it and put an analog to digital converter. So we know exactly how much zoom in and zoom out the person has pressed. So we now start sending the zoom in and zoom out value together with the position and the orientation of the camera lens to the rendering machine. So when the person holding a camera see the view in front of him, all the movements that he makes will be reflected accordingly, and that will be shown in the virtual world that's in front of him as well. I have recently learned 10 years on, that becomes the Hollywood way of shooting videos, except they don't have a projector screen like what I did. Instead, they have a LED, because now LED became so fine pixeled that if you start shooting a video by capturing image from an LED, that's actually turns out to be a much better approach than having a blue screen or green screen, then edit your virtual scene later on. Yeah. Okay. So now with deep learning, things are very different. I will be able to do things in a much more robust and efficient form. And the tracking can be done much more elegantly by combining more cameras, and I'll be able to control more mechanical cameras at the same time. So this work was about 10 years after when I did the system, when I made the system without any deep learning algorithms or GPU support. So here was the system, which probably we built, rebuilt around 2017. This time around, we are simultaneously controlling 4 static cameras and also 3 Pentil zoom cameras, mechanical cameras at exactly the same time. And that's my postdoc engineer down there. So what we did is that we have 4 static cameras, and the tracking is actually done both on the body as well as the head. If you sort of see the 3rd camera view, I'm not sure if you can see the lighting very well, but we deliberately turn off the GPU support. So there's actually a little bit of a detection lag. Let me actually just replay that. So if you just watch very carefully about the 3rd camera view, you can see that the detection not as smooth as the first 3. Because we just wanted to demonstrate that without GPU support and the processing cannot be done as efficiently compared to when you have it. So having this capturing system, now what we did is that we did another work where we tried to recover people's 3D pose without them wearing anything special. right? So it's actually called markerless tracking. So, or the markerless post determination. So the idea is that if you wanted to obtain the 3D pose from a pair of images or multiple images of 2D poses, the same person needs to be seen by at least 2 cameras, okay? Otherwise, you'll not be able to recover the 3D pose. You know, we developed our own unique way of matching people from this camera view to that camera to say these 2 are the same person, these 2 are the same person. And by doing that, we are able to then generate, or sorry, compute. I shouldn't use the word generate because it actually meant very different thing. I will be able to compute the 3D pose from the 2D poses detected in multiple camera views. Okay, yeah, so, and as you can see, that's the improvements, much significant improvement in terms of computer vision by utilizing both the GPUs as well as the, you know, the deep learning algorithms that's available to us today. So obviously, you know, you can't really do it with the deep learning algorithm alone. You've got to have a very large group of PhD students and engineers. And also you need to have very high-end graphic cards. So by the way, that was my team back when I was in Australia. Right now, I do not have any PhD student. So let's coming back to the natural language processing. So which is the second stream of the things I'm going to talk about. So in terms of NLP, you know, the example I'm going to raise, the state-of-art example, obviously is ChatGPT, right? Which is dominating the news at the moment. And I'm sure that's something that you are very looking forward to in this particular talk. And before we sort of jump in, you know, jump the gun to talk about the ChatGPT technology itself, I want you to realize this. Now, ChatGPT essentially, or removing the chat part, just looking at GPT. GPT is essentially a very successful language model. So what is a language model? Language model is this. Given that you have seen 20 words, a language model will tell you the probability of the 21st word, okay? So amongst your entire vocabulary, it will assign a probability to each one of these 40,000 or whatever words in the vocabulary, the probability of the 21st word, okay? So that's all it does. Now, please do not think training a language model is very hard or very expensive. Yes, training a very good general purpose language model is very, very resource consuming. But if you want to train a very small language model, that's actually quite doable. So I'm going to show you an example of a language model that I have trained. So a long time ago, that's like, yeah. So let me share my screen as well. So a very long time ago, I did a project for the one of the states government in Australia. We are looking at the relationships between the job advertisement. So we're looking at the relationships between the vocational education training, which is the training given to adults, and looking at the trend and the relationship with the job market. So in order to, you know, do this research, I was looking at using natural language processing to start matching between the job advertisements and the training courses, because training course description contains a paragraph of words, and the job advertisements also containing a paragraph of words. So you can use natural language processing to start matching between the two. Yeah, so that's the idea. And when the project has finished, when the project has completed, I've got something like 140,000 job advertisements sitting in my Google Cloud. So I was telling my engineer, I said, let's actually do something with it. And we said, how about let's start training a language model from it? So that's what we did. So we trained a language model that if you press enter, it's actually going to generate the next 5 words. It's a little slow because we are actually running on the Google Cloud, and it takes a little bit of a warm up. So yeah, just it will come up eventually. And then if you don't like some of the words that it's been generated, you can delete and you can get it to generate again. Yeah, so it just takes some time. Okay. Maybe what I will do is I will. Okay, so it comes up. So once it starts up, it should be pretty fast. And then you press the enter again, press space again, you'll be able to generate the next 5 words and so on. Okay. Yeah, it's actually usually a little bit faster than that, but just slow. Okay, it's coming up. So if you don't like some of the words, you can just delete and you can get it to generate. So because I trained the corpus from the job advertisement, so any words it's able to generate, it will also be within the context of job advertisement. So you're not going to get to do things like ChatGPT, and which is a very general purpose, you know, a word model, so that it obviously trains with a much larger corpus than us. So yeah, I mean, if you want to play around, you can actually go to riddle.com and you can press one of those, you know, icon, and you can start generating. Just be mindful that I'm actually paying for the Google Cloud, so don't use it too often because it will track lots of expenses for me. Okay, so yeah, let's just keep on going. All right, so and also I'm not sure if you, oh sorry, yeah. I'm not sure if you have seen it before. Has anyone ever seen a Google Duplex? It's actually been a few years. It has been around for a few years now. So Google Duplex is, they did a demo where they have shown a very human-like interaction when you are calling a shopkeeper and try to make a booking. So let me show you.
The progress of that system.
So,
for a client. I'm looking for something on May 3rd. Sure, give me 1 second. Sure, what time are you looking for around? At 12 p.m. We do not have a 12 p.m. available. The closest we have to that is a 1:15. Do you have anything between 10 a.m. and 12 p.m.? Depending on what service she would like, what service is she looking for? Just a woman's haircut for now. And we have it 10 o'clock. 10 a.m. is fine. Okay, what's her first name? The first name is Lisa. Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd. Okay, great. Thanks, great. Have a great day. Bye.
So I'll show you the second example, and now very quickly. The second example is actually even more impressive than the first one.
Hi, I'd like to visit people for Wednesday the 7th.
For 7 people?
It's for 4 people.
4 people when?
Next Wednesday at 6 p.m.
Oh, actually, we need to for like after like 5 people. For people, you can come.
How long is the wait usually to be seated?
When, tomorrow or weekday or?
For next Wednesday, the 7th.
Oh, no, it's not too busy. You can come for a week, okay?
Oh, I gotcha. Thanks.
So, I mean, the speech synthesis that's being presented in this demo is actually very impressive. I mean, it's very human-like, but it's still very far away from having a general purpose chatbot. if you think about this particular setting, when you are trying to make a phone call to do a booking, your conversation or the amount of conversation that you can possibly have is actually pretty limited. So within a specific domain, the chatbot can be done very, very elegantly. But if you extend the conversation, if you extend in the domain of the conversation to be a much bigger space, then the same level of human-like interactions cannot actually be achieved that well. I mean, for those of you who actually have used ChatGPT, you probably have experienced that too. The word generation is very good. The amount of information it has is also impressive, but the interaction of the between the human and the machine isn't as fluid as if you are talking to someone, if you're talking to another human. So in terms of, even ChatGPT has been around, and, there's still a lot of research that needs to be done in the NLP. And that was the last research project that my ex-PhD student have done, is to looking at what we call the multi-aspect sentiment analysis. So traditionally, if you are performing a sentiment analysis, it's usually onto the entire sentence. So if you're looking at a sentence, you would say this sentence is actually present itself to be positive or present itself to be negative. So in this particular setting, this is called the multi-aspect sentiment analysis. So if you read that sentence, it says the decor is not special at all, but their amazing food makes up for it. So in here, there are two separate entities. The first entity is the decor, and you can see the decor, the sentiment polarity is actually negative. Sorry, there's a lot of terminologies that are actually designed by machine learning and natural language people. So it's called the sentiment polarity. The second entity is food, and the food is actually positive, right? So you simultaneously extracting all the entities from a single sentence and now assigning a sentiment polarity for each one of them. And that's called the multi-aspect sentiment analysis. So yeah, and that sort of research is still ongoing in the NLP area as well. So let's move on to talk about the next bit, which is the generative model. And for those of you who are actually familiar with things like VAE, GAN, and the normalized flow and this kind of frameworks, they all belong to the technology of generative models. By the way, I have a fairly complete, in my view, very complete mathematical description of all the things that I've talked about today. So they are actually, you can download them from my GitHub website, which I actually have the link for you towards the end of the talk as well. So if you, if people have people seen that before, DAL-E, and especially DAL-E2. So if you're using DAL-E, by inputting a sentence, you are able to generate an image. Try to describing the sentence, depicting the sentence. Yeah. So one of my ex-PhD students has done something like that as well, except we don't have the amount of training resources that OpenAI has. So we train on MS COCO dataset, and the MS COCO dataset has got both the image as well as the description. So we took advantage of that. And so here's a piece of work that the other student of mine did. So this is, we try to do a cross-domain translation. By the way, the translating things from different domain in machine learning, it's called cross-domain translation, which the name sounds very intuitive. So you are try to translating, like DAL-E, try to translate from a natural language to image. Yeah, so image and natural language are two different domains. Now we try to do a similar sort of work, but translating a natural language to an animation. So this is the input sentence, which is not part of your training data. And this is the corresponding animation. So in order to do this piece of research, I have asked the student to essentially creating a data set from scratch because we couldn't not see available anyone have ever created a data set for that. The person, so the person actually spending quite some time creating the data set by essentially having hundreds of different descriptions of interaction between two people, and they just become actor to act on these two, performing actions according to that particular description. And it's actually very, very time consuming. So the level of accuracy obviously is depending on how much data you'll be able to feed into your system. And that's the sort of the best we can achieve at this present time. Okay, so here's another example, interesting example in terms of multimedia is the music generation. I'm going to play that song for you. That's has been a few years old now. So this is the AI song that written by Sony entirely by AI. Okay, I'm not going to play the entire song. You can actually search them on Google. Here's also the Google AI song. So yeah, I mean, hopefully ChatGPT one day will actually producing a very viral song. I mean, there are apps that actually does that already. To input a first few sort of notes and it will actually complete the rest of the song for you. So I'm yet to sort of see how great they are, whether they can write the next sort of viral song on the internet. So a few years ago, we also did something around the music generation. I had this idea of if you input the one hand play of a piano. And then the machine will translate into two hands play. What does it sound like if you have played by two hands? So I'll play it again. So that's the input of one hand play. So that's the what happens if the person play by two hands. Okay, so does anyone know how I did it? Specifically around how do I collect the data? So the way I did it is actually a lot simpler than you think. All the data I grab from internet already has two hands play, and they are in MIDI form. They are MIDI files. They are MIDI file format. So I use the software that are able to separate a MIDI file into two channels, the left and the right. So then I took all the right hand play as the input. I took the original two hand play data as the output. And here you go. I have get myself a full data set without any human labeling, that's a key, right? Otherwise, a lot of people think that I just go to a music studio and recording people's play. No, that would be too expensive. Okay. So the last stream of machine learning or deep learning I'm going to talk about is deep reinforcement learning. Does anyone know what reinforcement learning does, or have heard about it before? So if you haven't, but I think you probably have heard this AlphaGo from Google DeepMind, how they have designed a AlphaGo algorithm that beat the best Go player in the world. It is possible to, even in the late 1980s, IBM has built this Deep Blue machine that beat the best chess player. But that's not using neural networks. What they did is that it's a supercomputer. They exhaustively search every possible movement and figure out what are the optimal move. But you can't do that. You can't do that same thing with Go because the number of movements is just so much greater than the chess play. So what people did from AlphaGo is they use some reinforcement learning. And I do have a full description of how the algorithm works in my GitHub site as well, for those of you who are interested in. So, you know, and that kind of brought reinforcement learning into the sort of the attention of the machine learning community. Deep reinforcement learning has been around for decades. It's only until sort of, you know, AlphaGo's victory that actually made a lot of people start jumping on researching in reinforcement learning. So we kind of also jump onto the bandwagon by joining one of the competitions. So this is a, I mean, I'm sure that people know what RTS is, right? So it stands for real-time strategy games. Do people play games like StarCraft or League of Legends? Yes? I mean, no? Okay, so everyone studies very hard. So these type of games called real-time strategy game, but obviously, as a researcher, as a university scholar, we can never have the computation resources to compete with, say, OpenAI. OpenAI has got the software called StarCraft, AlphaStar. Obviously, it's a game agent that actually competes in StarCraft, and actually did very, very well too. So because we don't have the similar kind of resources, now one of the scholar, he did us a favor by creating something called micro RTS. So it's an RTS game without having any graphics at all. So that's a graphic, well, has minimal graphics, but it has all the quintessential elements of a real-time strategy game. So you have like the cavalry, you have the infantry, you have the air force, you can also build the bases, you can also shooting each other and things like that. So that's a framework specifically for scholars to submit their game agents and to compete with each other. And so it's part of a conference called the IEEE Conference on Games. And we actually joined in the competition in 2019. And that was our win rate. So we significantly beating the second player. But I don't want you to think this is a very, very large competition. It's actually a fairly minor one. It's part of the many possible competition you can join under the IEEE Conference on Games. But nevertheless, it's always a good feeling to be able to come first. So because we're going to talk about ChatGPT, and ChatGPT utilize reinforcement learning to some extent. So that's why I wanted to spend just 1 minute to talk about reinforcement learning and how that differentiates with supervised learning. So just imagine that you have an image, and a human can very easily label this image as an elephant, okay? Human can do that. But if you look at the same thing, like a image of a Go board, right? An image of a game of Go in that particular setting, a human is very difficult for a human to say, I am determined that white is going to win, okay? Or I'm very determined to say the white is going to lose. You can't actually tell that. So the difference between reinforcement learning and the supervised learning is the following. In terms of when you're actually dealing with a problem that can be solved by reinforcement learning, usually there's only reward signal. There's no instruction label, okay? There's no instructional label. And also, unlike supervised learning, all the data is available at exactly the same time. I mean, all the data is available at training time. Now, with reinforcement learning, that's not the case because the data is not available until you make an action, okay? And the action that the agent takes is going to affect the data you're going to receive subsequently. So for example, if you're going to place your piece in here, and then you're going to receiving data that's kind of around the vicinity of changes in that particular board. So the action you take, it's going to influence the data you'll be receiving subsequently. And also, the data is not RID, yeah? Because if you think about it, by playing, the stone in certain places, the next board will be very similar to the board that you receive. However, in supervised learning, in most of cases, you can actually swap the orders of the data. You can name this data being, data number 2 and that data being number 5, and you can swap the order. and it's not going to change your algorithm. So the data actually form a set. Okay. So when you have this kind of settings, you need to solve the problem by using reinforcement learning rather than using supervised learning. Okay. And in terms of reinforcement learning, what you try to do is try to work out a policy in such that by taking the next action, it's going to maximize the average future return. Okay, by taking the current action, which is going to maximize the expected future return. And for those of you who are doing economics or doing finance, you say, okay, that's exactly what a lot of the trading strategies evolved around, isn't it? By taking the current action, how do you maximize the average future return? Okay, yeah, it's a very similar sort of a goal. And also, please do not think that AI and machine learning are just limiting to, the large internet giants or within the university research. AI and machine learning and data science research is pretty much everywhere. Here are the technologies I have used when I did a lot of industry projects when I was in Australia. So in the last 6 years, I have worked with 14 separate companies, over 24 different industry projects, individual projects, and these are the technologies that we have used. Okay, all right, so I will keep on moving. And for those of you who eventually will be taking a career in AI, well, the news, the news is great, because there's actually quite a lot of jobs out there, and AI is still a very demanding skill set to have. Doesn't matter where you are around the world. Okay, so that sort of concludes the general introduction of deep learning. And do we have any questions before I will talk specifically around natural language processing and most importantly of it all, ChatGPT, or the technologies leading up to ChatGPT? So do we have any questions? No? Okay. Well, if you don't have any questions, that means that you are, comprehending the material very, very well. All right. Or you're just shy. Okay. All right. Okay. So I'm just gonna keep on going. But if you do have questions, please, let me know, or you can just leave till the end and ask me questions in the end as well. Okay. So now if you look at, data, if you look, a lot of the examples I talked about is around computer vision, right? Computer vision, which involves the data of an imagery forms. So if you look at an image, and there's a difference between an image and a piece of natural language. So what's the major difference is that if you have an image, that image is already in numerical form through the pixels values it has, yeah? So every single pixel has got, a numerical value. And when the image is color, then you usually have 3 channels, RGB or YUV or different, depends on what kind of color channel that you define the image to be. But the natural language has got no numerical value. What you have is a set of tokens. These tokens are actually nominal, means that you cannot compare with them. You can't actually do any arithmetic calculation. You can't just simply say, if I add this word with that word, what do I have? You can't actually do that, right? Whereas pixels, you can. You can actually adding or subtracting 2 pixels together, right? And by the way, people do that all the time, because if you wanted to work out whether the background has changed, they will take the current video frame and minus the last video frame. But you cannot do that with natural language. So the history around NLP is revolved around how do we actually changing these tokens into numerical representation, i.e., how do we convert them into a vector? So the simplest sort of approach of converting into a vector is design what we call the one-hot vector. So the one-hot vector is this. The first letter, sorry, the first word, I should say the first word in your vocabulary, you're going to assign a vector to be 1, followed by all the zeros. And the second word will be 0, 1, then all the zeros. The third one will be 0, 0, 1, then all the zeros. Okay? We call them one-hot vector because there's only one 1. The rest of are all zeros. Okay. And well, that kind of is intuitive and it's easy, but there's a lot of downside with it. And you can pretty much tell that if you do that, your structure is extremely sparse. So what I mean by that, sparse, it just means that you have lots of zeros, only one, only a few ones. And secondly, you can't actually compare the distance between these two representations. Why? Because every pair of vector, their Euclidean distance is precisely √2, okay? They're all exactly the same. So that's not very, very useful for that. And so therefore in 2013, so this researcher at Google, he came up with this algorithm called word2vect. And by the way, natural language processing is evolving so rapidly that anything that's 10 years old is considered to be very, very sort of ancient. All right, so that's why that's the first slide I'm going to show, 2013, right? So what it does is that the underlying principle is to say, if I want these two words to have very similar representation, then the surrounding of these two words, when they appear in a whole bunch of paragraphs, got to be similar. Okay, so that's a very sort of intuitive and assumption, isn't it? If these two, if the representation, if the numerical representation of these two words are similar, it also means that the surrounding words are going to be very similar. Yeah. So utilizing this particular, a principle, this person have came up with word2vect algorithm, and then eventually you are able to obtain a set of numerical representations of these words. So not only they are meaningful, but you can also performing arithmetic calculation on these word vectors. So for example, the difference between a woman and a man is the same as the difference between a queen and a king. By the way, that's the diagram I got from the paper, right? So, that's the illustrative diagram I got from the paper. All right. And for those of you who might be interested in how do these vectors look like, and there's a link below. By the way, the PDF of the slides is actually on Moodle, so you can actually download it and have a look at it. So people have a very nice visualization on TensorFlow Playground, which is also done by Google. You can visualize all the 10,000 words when they are in the vectorized form. But obviously they do something called dimension reduction. Otherwise, you can't see them in 3D because the word vector is generally 200 in dimension. Or I can't exactly what dimensionality it is, but it's actually quite high. Okay, so let me actually just show you very, very quickly. By the way, I removed every line of mathematical equation in this presentation. But in order to supplement your understanding, I'm not sure if you have looked at your Moodle, there is a mathematical explanation to every single thing I talk about around natural language processing. So have a read about that as well if you are interested in the mathematics behind it. So algorithmically, what it does is this. Imagine this is a sentence, and you might have a window size of 3. So you firstly start to looping through the sentence by a window of 3, right? So you grab the first 3 words, grab the next 3 words, grab the next 3 words, and so on. And all the center words become the target, and all the surrounding words become the context, okay? So from here, you can construct, these are the target words, and these are the context words, right? That's simple to do. And once you've done that, you want to find their representation, their numerical representations, such that the probability of context given by the target is going to be maximized. That's it. That's basically the whole design philosophies around word2vec. But there's a couple of things I would like you to take notes. You can see that every word will have both the opportunity of becoming a target as well as becoming a context, right? It can be the context of other target words, or it can be a target word by itself. Yeah. So just be mindful of that. All right. So you can see that if they appears a lot, if these context and you know, the target pair appears a lot, then the probability will be higher. Yeah. Okay. All right. Questions about that? Okay. Oh. Okay. So here comes in sort of the next mini milestones of natural language processing. This is where all the internet giants want to improve their translation engine, right? And I think if people have been using Google Translation over a decade, you probably have realized that the translation becomes much better after 2016. And because in 2016, the Google has essentially changed the entire translation mechanism to be using the algorithm on the right. So it became entirely neural network based translation, as opposed to the statistical you know, translation that people have been working on for many, many years. And what I have also heard, which is it's unverified, that there's only a handful of engineers have actually designed the sequence to sequence with attention mechanism, and only takes us several months of development. So yeah, it's actually quite incredible. But before we talk about this, I wanted you to think about this. So this is the sort of the starting point of all the neural network based translation. It's called the sequence to sequence. That's what I like about papers published by Google. They are very intuitive, right? Sequence to sequence. And so what it does is this. It actually takes this is your input sentence, okay? So this is the output sentence. It firstly finds out all the numerical representations of all the input words, and they call them encoder. And all the numerical representations of every single word in the language you want to translate to, and that's called the decoder. Hopefully that's also intuitive, right? Encode, decode. All right. So now how this system works is the following. They run something called recurrent neural networks. Recurrent neural networks is specially designed to process data in a sequential form, okay? So I'm sure that you understand the difference between a set and a sequence. When you have data in a set, you can swap the orders and do not influence the model. But if you have data that comes in the sequence, you can't simply change the orders. Like a stock price, you can't simply change the orders, because otherwise, if a stock goes up, if you change the orders, reverse the orders, it means the stock goes down. It actually tells you a very different story. Same thing with the natural language, okay? Because the sentence actually comes in order, right? You can't simply swap the orders of the letters around. Okay, so what a recurrent neural network does is the following. It tries to propagate information from the left to right through the changes of values in the neurons, okay? So that's just mimicking how the human reads a passage. You read from the left to right, yes? And once you're reading from the left to right, you essentially have a summary of the input sentence, yeah? Okay, so just to make its algorithm slightly better, people tend to use something called a bidirectional recurrent neural network, which means that not only you are reading a sentence from left to right, the machine also reads from right to left, okay? But the moral of the story is that once you actually read it once, left to right, and right to left, you will obtain a summary of that sentence, okay? And you then take the summary of the sentence, you put them into an encode decoder, and you start generating a whole bunch of words. These words will corresponding to the sentence that you want to translate to, okay? Does that make sense? Okay, so, you know, in the, and that's how it works. And basically in the, using analogy, when I'm preparing these notes, I thought the best way to present them is using analogy, and hopefully some of the analogy actually makes sense to you. I have to admit that it's actually a lot simpler than to show you using equations than analogy, but it's also fun to present them in a pure sort of non-math fashion. So the analogy is this, is that when you're translating, you start reading the input language once, okay? And you actually sort of remember what the input sentence tried to portray. And then you take the knowledge, start translating, okay? That's what you do, with sequence to sequence. So the result obviously has much room for improvement. And that's why the following year, 2015, people came up this a framework called attention. So what attention does is that, let me using another analogy, is to say, what if people don't have such a good memory? You know, when you sort of reading the input sentence, you try to remember what the sentence tried to say, and then you translate. But what if people don't remember the input sentence that well? How about when you translate, not only that you took the summary of the inputs, when you try to translate every single word in the decoder, you're also going to have a glance at every single word in the encoder, okay? Right? So, you know, when you try to translate this word, you're going to say, not only that, you know, you have the summary, which is you gain from your running your recurrent neural network. What if you have direct access of every single word in the encoder again? And because every single word in the encoder will have a different contribution to the words that you want to translate, by calculating accurately the amount of contributions from the words in the encoder, you are actually going to get a very sort of robust translation, okay? And the amount of contribution, people came up with a special word for it. And it's very important that you remember this word. It's called the attention. So if you go to Google and start searching the word attention in natural language processing, you can find thousands of articles. The word attention is basically the amount of contribution of some elements towards the word that you want to generate. Yes? Okay. Hopefully that makes sense. Yeah, so that's the difference between the two. Okay. Now let's go to the next one. I know it's a bit overwhelming because I'm trying to summarize the whole 10 years of natural language processing in half an hour. So hopefully, so thank you for being with me. The next thing is so fundamental that everything that you will read about in terms of natural language processing in the news has got something to do with this. It's called the transformer. Again, it's a word that invented, I mean, obviously transformer means very different things in many different contexts. And I'm even not even sure whether transformer is the best word that Google can think about. But again, that's just the word that people use. So, and imagine now we have a very different way of reading a sentence. Okay, so I said before, you know, the recurrent neural network is essentially a person reads a sentence from left to right and right to left once. Okay, and that's sufficient. Now, what if we have an entirely different way of reading a sentence? What we do is this. We have these 5 different ideas. And hopefully the way I'm explaining will be making a lot of sense to you. So the first idea is this. When you're reading a whole bunch of words in a sentence, you try to figure out the relationships between every single pair of words. Okay, that's what you try to do. You try to figure out what is the relationship between the first and third word, first and fifth word, and first and seventh word. And by knowing this relationship, you will have a deep understanding of every single word in the sentence. I'm not asking you to concur with me. I'm just asking you to, I'm just asking you to sort of, knowing what I'm talking about, right? So whether you agree with me or not, that's another story. But just for today, try to, sort of understand the mechanism that I try to describe, and hopefully you will also agree, okay? Because the performance is outstanding. Okay, so now let me repeat. The first thing you do is that you find out the relationship between every pair of words, so you have a deep understanding of these words in a sentence. Now, with this deep understanding, you try to repeat the process. You try to find the relationship between pair of words again. Now you have an even deeper understanding of those words. Now you try to repeat the process 12 times or whatever times it takes, so that eventually you'll have a very deep understanding of those words in a sentence. Yeah? Okay. So that's kind of captured in the first three ideas. That's how a machine will read a sentence, right? By finding out the relationships between every pair of words, but you do that multiple times, okay? So eventually you're gonna have a understanding which is so deep that's the best representation of your sentence. Cool. All right. So now we have the fourth and fifth idea is the following. Now, when a person reads a sentence, you can be biased, right? You probably have your own interpretation of the sentence. So why don't we ask 6 people to come on board and get them to read the sentence in exactly the same mechanism, but with a different sort of understanding, yeah? And if you do that, in the end, you try to combine 6 people's summary of the sentence together. Now that will be a very robust representation of the sentence, okay? So now the understanding from all 6 people by multiple rounds of relationship finding of those words will become a very robust understanding of the sentence, okay? So hopefully that makes sense, because that's exactly what Transformer tries to do. And Transformer tries to do that. So here's a diagram I want to show you. So the first 3 ideas are encapsulated in here, right? So mathematically, what it does is the softmax function, Q and K transpose, then times V. And why that's the case, please check out my accompanying notes on Moodle, which actually has all the mathematical explanation on why this thing actually encapsulates the first 3 ideas, all right? And the second idea, when I talk about the second main idea, which is idea 4 and idea 5, which we ask multiple people to read the sentence, right, in the same mechanism, is encapsulated in this particular diagram here. So if you read the literature of Transformer, you will know that this is referred to as multi-hit attention, okay? By the way, there's a lot of new terminology came up in NLP, and I apologize for that. But once you sort of get used to it, it's actually not that confusing. And I can guarantee you there will be a lot more new terminology came up in this particular area. Okay, so that's it. So that's pretty much Transformer. And Transformer essentially revolutionized in the last 5 years the entire natural language processing sphere. So, and again, this is how we put a transformer together in an encoder and decoder setting, which is kind of the same of where we have shown you before. Remember, previously That's our encoder, right? Using recurrent neural network. And that's our decoder using recurrent neural network. And this is the transformer encoder and transformer decoder. Now, just one thing people probably are wondering, if you find the relationships between pair of words, then isn't that you start to losing the order of the words? Yeah. If you find the pairwise relationships, you know, this is different to the recurrent neural network where you start propagating information in that specific order, either left or to right or the right to left. So to compensate the losing of position information, what people did is to come up a position embedding. So basically, if you have the first word, you're going to put 1, you know, as a label for, as a position embedding for the first word. If you have the second word, then you put the position embedding of 2 in the second word. I mean, it's actually slightly more complicated than that. They don't just put the number 1 there. They actually generate a feature vector that corresponds to the letter 1. I mean, the number 1, the position 1. They also generate another feature vector of a multi-dimension vector corresponding to the number 2 and so on and so forth. Okay. And also when you are performing the decoder, because you still try to generate 1 word at a time. And so there's an engineering trick to it. So basically what they did is they use something called a masking. I don't have a diagram for it, but what it does is that if you masking out the words, the position that you want to generate, that's sort of simulating that you cannot see the future words when you are generating 1 word at a time. Okay, so basically that's the, you know, framework corresponding to the encoder decoder of the recurrent neural networks. All right, so what can we do with transformer? So when it's proposed, a year later, Google came up with this thing called BERT. So if anyone sort of tracks the, does anyone like Sesame Street? If you do like Sesame Street, you will find that a lot of the NLP algorithms are named after Sesame Street characters. So there's a Bert, there's Ernie, right? I didn't talk about Ernie because otherwise the talk will be very, very long. Actually, I need to finish in 30 minutes. So I will be wrapping up quickly. So what BERT does is that it's actually an encoder. So it tries to using the transformer framework to have a much better robust representation of the words than the word-to-vect. So if you do recall, the word-to-vect, using the word-to-vect algorithm, remember that's a 2013 algorithm, every single word will have exactly the same embedding. But that's not actually very useful, isn't it? I mean, if you look at the word bank, she walks along the riverbank, or she works at the investment bank, even though it's the same word, but the meaning are very different. So therefore, when you start embedding the words, you actually also need to look at its context as well. So that's what the BERT algorithm tries to achieve, is try to achieve a embedding such that you will have a context. All right, so it actually does this very, very cleverly through supervised learning. But you don't actually want people to start labeling data on natural language. Believe it or not, labeling images is actually a lot cheaper than labeling natural language because you have to read it. Image, people just glance at it, you go, oh, okay, that's an image of a cat, that's an image of a dog. For a natural language, people have to read the sentence, actually much, much slower. So the way it does is this, at this input sentence, it will masking out 15% of the words. And because it knows what the word is, then you just ask BERT to actually predict the things that it actually masks out. It's actually quite clever, isn't it? You already have the sentence. You just masking out the first words, and you use the BERT to actually predicting the things that you try to mask out. So I have this sentence example for you. I say, Gong Tou is a popular something in mirror. Okay, so obviously you do know he's a singer. So the correct prediction must be singer. Through this learning or predicting the missing words, you're actually gonna achieve a much robust, sorry, I keep on saying the word robust, but you achieve a good representation of these word representation for these words. Again, it has another sort of a task, another sort of a supervised learning task without any human labeling, without human label. So it's called the next sentence prediction. So if you give this example to say, the first sentence is to say, Gongtou is a popular something mirror, so is Yang Loman. You obviously that this sentence is the next sentence of this, right? So they appear together naturally. And if you say Gongtou is a popular singer in mirror and the weather is very nice, obviously they are two separate sentences. They don't talk about the same thing. So the label should be not the next sentence. And so this kind of training data is achieved without any human labeling because you already have the passage. So you know which sentence is actually followed by the other. Okay, so here comes the sort of grand finale of today's talk. I've only got 2 slides to go. So I'll give people, I think a lot of people are start to feel the relief. There's only 2 more slides to go. So the traditional way of performing, remember what BERT does. It doesn't do any tasks. All it does is translating or transforming your sentence into a vector representation, into a numerical representation. That's all it does. So it doesn't actually solve any of the natural language processing tasks for you, okay? So then if you want to solve some, what we call the downstream task is after you have converted the sentence into numerical representation. Now, let me pick a particular downstream task, sentiment analysis, okay? Let me pick a sentiment analysis. So if you input this sentence to say, I love #1 seed, okay? Right, which is a song by Gongtou. So I love #1 seed. And if you put that sentence into the encoder, it actually will generate the numerical representation for it, okay? And then you need to build a separate model, like a sentiment analysis, to sort of say this sentence is actually positive, the percentage of the sentence being negative, okay? So you need to build separate models for your for any downstream task you want to achieve. And people said, okay, I mean, that's the traditional wisdom, right? People do that. Up until about a couple of years ago, people still do that. They're just using a very good embedding algorithm. But what's after the embedding algorithm, you need to build separate model for it. So people said, okay, if the natural language generation, if the decoder is so good, then why do we need to encode it again? Yeah. So why can't we change the downstream task and we try to solve this in terms of a natural language generation alone? Okay. So that's how people do it. So what they did is they first built this template to say if the input followed by these words, it was A, then followed by another word, which you try to predict song. Okay, so as long as you're putting the input in, you can ask the machine to predict or to generate what this word will be. So they, without having any extra model, like the case we have built in here, they now just having a language model. A language model itself is able to solve a problem for you. So hopefully that makes sense to you, because that's essentially what GPT tried to do. Okay, so it's a language model. The language model itself can solve a problem for you. Right. So in the case of here, you say, I love #1 seed. It was A. If the generated word in the spot of Z is excellent or great or wonderful, then you'll say this is a positive sentiment. If the generated word is bad, awful, or silly, and you will say it's a negative sentiment. So you actually try to use natural language generation, and the language model try to solve a problem. Okay, no more separate sort of development of models, and this is something called zero-shot learning. Okay, because you do not need to train extra parameters. You just take a language model and solve the problem for you. Now here comes the case of GPT. It tried to do the same thing for question and answer. Now the input sentence is how many members are in the band mirror, right? And then if you can, from here, if you can generate probabilistically what are the next set of words, you are actually going to get that. And the machine is so clever that it actually understands the input sentence will be the appropriate prompt, such that the generated or the rest of the sentence, they form the answer corresponding to your question. Does that make sense? Okay. So you are now trying to use a language model and the word generation mechanism to be able to generate an answer which forms part of the second part of your sentence, which answers the question which formed the first part of your sentence. Okay, and that's the idea. Yeah. So having a really wonderful language model and plus the prompting idea will embed it into it, you now can actually start answering questions by just keep on generating words from your question. Okay, all right. So that sounds wonderful, isn't it? And so let me very briefly talk about GPT. So what GPT does is that, you know, it trains, it's a language model. So as I have repeated many times, a language model just to say, having these input sentences, sorry, having these input words, what is the probability of generating the next word, right? And because I'm running out of time, so I'll very quickly talk about them. So you have essentially two phases of training. The first training is essentially try to figure out what the parameters are so that you will maximize these conditional probabilities. So, you know, because the second word is depending on the first word, and the third word is depending on all the preceding words, and the fourth word is depending on the word 1, 2, and 3. Okay, and also by calculating these probabilities, you'll be using the transformer framework, which I have talked about it in length 3 slides earlier. Okay. So, and then what it does is that it will use some kind of fine tuning. They call it supervised fine tuning, and it will get GPT to solve some of the tasks. So the tasks including things like classification, the alignment, entailment, and similarity and multiple choices. So these aren't actually the labeled supervising tasks for the GPT model to fine tune its parameters. Okay. All right. So the last thing, this is the absolutely last slide I want to talk about, is this. So we've been talking about before to say the answers are actually generated from the questions that you ask. So if you ask the machine, if you're using ChatGPT and asking a question to say, who sings the song number 1 seed? And the machine then take this sentence and start generating the next few words. Okay. So because it cannot generate things that it hasn't seen, for the data it grabs from the internet, maybe somebody has answered this question to say Gongtou, right? Or other people will say, you know, after they see this question, so who sings the song number 1 seed? The people will say, I don't know, please tell me. Right. So this is not a very useful answer. And this is a useful answer. Yes. And because by having just a language model, the machine cannot tell which answer is good or bad, because they are equally good. But it does not actually know which answer is human prefer. So how do we do that? So what we did, I mean, what not me, what OpenAI did is that they actually get a lot of human involved to give a score. So when you see a question like that, if with some high probability generating these couple of answers, right, it will actually say this is the preferred answer and this is not. And then remember reinforcement learning, right? Using reinforcement learning techniques, it's able to fine tune the model so that the machine now actually understands by reading this type of answers, by reading this type of questions, what is the appropriate answer I should give that will be enjoyed by a human, as opposed to something that I've seen before, but is not very useful to human. Okay. So that's where the reinforcement learning actually comes on board. Just sort of, I'd like to say that the technical paper about ChatGPT has not released by OpenAI yet. We suspect it will be released very soon. So the information that people can find is from a paper they had earlier. It's called Instruct-GPT. So we're kind of assuming no one knows what GPT 3.5 stands for, but people think that it's just GPT-3 plus Instruct-GPT. That's the sort of common consensus. All right, so that's concluding my talk. And if you actually want to know more about machine learning and different aspects of machine learning, especially the mathematics around machine learning, you can visit my sort of never-ending machine learning knowledge dissemination website. And also this slide is also available in your Moodle as well. For the mathematics around modern natural language modeling, it's also in a Moodle. And a lot of the videos that I have presented can be found in this demo link. You can pretty much access all the research demos I have done. And I think that's it from me. I think I'm right on time. Thank you.